Hello everybody, I'd like to do some problems involving linear momentum in one dimension. Let's start with question 1. So a ball of mass 0.440 kilograms moves with a speed of 8.10 meters per second. And it has a head-on collision with a ball at rest which is 0.220 kilograms. Assuming that the collision is perfectly elastic, calculate the respective speeds and the direction of both balls after the collision. Alright, so let's see. Let's first draw this situation. Yeah, so we've got a ball. Let's call this ball A. So it's mass A, subscript A. And it has a mass of 0.440 kilograms. And it's moving with a speed, so velocity A. And this is 8.10 meters per second. And it's a head-on collision, so there's no moving off in different angles and so on. It collides with a different ball, which we'll call mass B. And this is 0.220. And this one is at rest initially. So that's just 0. So I'll just say at rest. So this is before the collision. After they collide, well, they're going to move off in different with different velocities and so on. And that's what we need to figure out. So at some point they're going to collide, and we want to find out what the speeds and directions are after the collision. So there's a few clues here that we have to find inside the text. And one of the clues is that they said the collision is perfectly elastic. Now what does that mean? Well, when we've got an elastic collision, let's do this. Elastic collision. This means that the kinetic energy is conserved. So kinetic energy being conserved means that the change in kinetic energy is 0. So I mean, let's just write this. So the change in kinetic energy is the kinetic energy after the collision minus the kinetic energy before the collision. So what are these? And if they equal to 0, then that means kinetic energy after is equal to kinetic energy before. So this means that the kinetic energy before the collision, I'm just going to write before, is equal to the kinetic energy after. And what is the kinetic energy before? So it will be of each ball. So the ball that's moving, it will be a half m subscript a, because it's that ball, we call it a, velocity a squared. And then we must add the kinetic energy of the second ball. And then what is this equal to? Well, it's equal to the kinetic energy of the second ball. The mass doesn't change. And then velocity subscript a, but we'll put a prime. So that little dash there to say prime, that little apostrophe or quotation mark, single quote, squared plus a half mb vb prime squared. So this we know is 0 because it's at rest. And these values, of course, we need to now start solving. So let's just simplify the equation a bit here. So now we end up with a half ma va squared is equal to a half ma va prime squared plus, so there's going to be a lot of algebra here, a little manipulations here and there, mb vb prime squared. So obviously all the halves cancel, so that's at least some simplification. But unfortunately we have too many unknowns, so we'll have to see what we can do here. So how would we want to simplify this further? So let's just write it. ma va squared is equal to ma va prime squared plus mb vb prime squared. So it might be a good idea to revisit the question, and let's just see here. But so we've got the two masses, and we've got the first velocity, the velocity of ball A. But now we have two unknowns. We don't know what the velocity of ball A is afterwards, and we don't know what the velocity of ball B is afterwards. So let's try to isolate one of the unknown variables. So we've got the two masses, and we know what VA is initially. We don't know what VA prime is, and we don't know what VB prime is. So let's try to get one of them by themselves. So let's go for VB. So now upon further simplification, we get MB VB prime squared is equal to MA VA squared minus MA VA prime squared. So I just subtracted MA VA prime squared from both sides. And now we can divide through by MB. So you can just put a comment if you want to, just to say divide by MB. So now we get VB prime squared is equal to MA over MB. And just to show that one more step, you can factor out the MA here because it's a common factor. So we have VA squared minus VA prime squared. And on this, we just do the same thing. We're just factorizing, it's just a little bit simpler. VA prime squared. So this is an equation, and I think it will be a good idea to label it. So let's just label it equation, we can just call it equation 1. So this is an expression for VB prime. Squared at least. But now remember this, we're dealing with momentum here, so momentum is also conserved. So to be specific, let's say linear momentum is conserved. And what does that mean? Well, it means that the momentum before the collision will equal the momentum after. So this means momentum, which symbol is P, before is equal to P after. So what was the momentum before? Well, it was the momentum of each ball. So it's mass A times velocity A plus mass B times velocity B. And this is equal to mass A times velocity A prime plus mass B times velocity B prime. Again, we know that velocity B is 0, the initial velocity, because the ball was at rest. Now we have an expression for VB squared. So what are we going to do here? Well, we can do again some additional simplification. So let's do it step by step. So we get MA VA is equal to MA VA prime plus MB VB prime. So in our equation 1, we have an expression for VB squared, not VB itself. So probably a good idea here is to get VB isolated as well, and then to square it, and then equate the equations. That might be a good idea. So let's try that. So let's make it MB VB prime is equal to MA. So MA, again, we can factor it out, is going to be VA minus VA prime. And then just divide through by MB, we get VB prime is equal to MA mb multiplied by va minus va prime. And then for good measure, to make the two equations equivalent, let's square both sides. So I'll just write the comment here to say square. So now we have vb prime squared is equal to ma over mb squared times va minus va prime squared. So let's call this equation 2. So both equation 1 and equation 2 are expressions for vb squared. So this means equation 1 is equal to equation 2. And this can only be true if ma over mb va squared minus va prime squared, and this is equal to equation 2, which is ma over mb squared multiplied by va minus va prime all squared. So notice you need to be careful. On the left hand side, the individual velocities are squared. The individual velocities are squared and the difference is taken. On the right hand side, the difference is taken and then they're squared. So the ma and ma over mb we can cancel a little bit. So let's do this. Let's simplify the left hand side to like this. Let me show you. So we go ma over mb, and let's use the difference between two squares. So we end up with a va minus va prime multiplied by va plus va prime. So this is the difference between two squares. Then here we have ma over mb squared, and then I'll just write this one here, va over minus va prime multiplied by va minus va prime, because it's just squared, so it's multiplying by itself. The reason I did this is now you'll see how nicely these things simplify. So on the left hand side, the ma over mb can go and the square can go on the right hand side, and then the va minus va prime can go, and the va, one of the va minus va prime can go on the side. So now we have va plus va prime is equal to ma over mb times va minus va prime. So a little bit more simplification needed. Let's get va prime by itself, then we can solve. So on the left hand side we'll have va prime, and then when we bring the one on the right hand side over, its sign will change from negative to positive. So it's plus ma over mb va prime, and then on the right hand side we'll have the ma over mb va, and then minus va, because we're taking the one on the left hand side, this one here, we brought it over the other side. So let's just factorize a bit here. So we get va prime into 1 plus ma over mb, and then here we can also factorize the va out, and we end up with ma over mb minus 1. Let's just do it step by step here. So I mean 1 plus this, so it's mb over mb plus ma over mb. So we end up with mb plus ma over mb. And then on this side we end up with va times ma minus mb over mb. Now we want to isolate va prime, so we end up with va prime is equal to mb over mb plus ma multiplied by ma minus mb over mb times va, and then of course the mb's will cancel here, and then we just end up with ma minus mb over ma plus mb times va. Now we've got all these values and we can plug it in. So let's do that. So ma was 0.440 kilograms minus 0.220 kilograms. This is all over the same values, but now we just plus it. So let's do this a bit quickly here. So that's 0.220 kilograms. And then VA was 8.10 meters per second. And if we plug this into calculator, we get 2.7 meters per second. So we know our units are right, because these kilograms will all cancel. So this is what the velocity of the first ball is after it collides. So what is the velocity of the second ball? Well, we can just go back to any one of our equations. So we can, before we had equation 2, we squared this equation here. We can just call it star this time quickly. So from star, we have VB prime is equal to MA over MB times VA minus VA prime, and then we can just plug in these values. So MA we know is 0.440. I'm not going to bother with the kilograms now, we know the stuff cancelled. VA, the initial velocity was 8.10, and then now it's minus 2.7 output meters per second here. And if we plug this into the calculator, this is 10.8 meters per second. So visually what happens after the collision is basically, so I'll just say after the first ball, which was MA, after it collides, it continues in the same direction, but now at a reduced speed, which is understandable, because it would have lost some energy, kinetic energy would have been transferred, and the second ball, MB, goes off in the same direction at quite a faster velocity, 10.8 meters per second. So what's happening is when the first ball, mass A, when it collides with mass B, there's a momentum and energy transfer. And because mass B is much lighter than mass A, in fact it's half the mass, it's understandable that it would move off at such a fast rate. It's actually moving faster than what the original ball was moving. The ball A was actually going at 8.10 meters per second, and now ball B is going at 10.8, which is even more. So this is conservation of energy and momentum. We'll move on to question 2. Thank you.